So before we move on to the sort of the next topic, and more stuff, vector fields and so on. So I wanted to mention or sort of formally introduce manifolds with boundary. This is something that will show up quite a lot later on, and this is something we need. I mean, so one example of this is something like a closed disk, right? So let's say in R2, and so that's certainly not a manifold, because if you look at a point on the the circle here that's bounding this region, so then a neighborhood of that point wouldn't look like a Euclidean space. So it will look like half of a Euclidean space, right? So if you kind of zoom in here, if you like, and you can probably sort of straighten the picture by a diffeomorphism, so that sort of your portion that you're looking at looks like sort of like a half disk. Okay, so that's this point. Let me color it red, the point that I'm centering around. Right? So you don't get a homeomorphism from an open set to an open set in R2, but you get an homeomorphism to some kind of set that looks like this half disk, right? So you need to kind of think about such sort of manifolds with boundary, with these things which have these half Euclidean spaces as neighborhoods. I mean, maybe let me just draw another picture. These are sort of surfaces with boundary, and a surface with boundary might be, so you might have a genus 2 surface, let's say, but then you have some boundary, and so this red portion is the boundary circle, right? So all along this red circle, you have these half disk neighborhoods, as we had in the first example. Okay, so just to formally introduce these, so we need to talk of this local model now being these half spaces. So I'm going to call that Hn. So that's this half space in Rn. So it's all the set of points in Rn, so that the last coordinate is non-negative. Okay, and so this is the model space for these manifolds with boundary. Okay, instead of Rn, sort of as a whole, and then this is sitting inside Rn, so it gets a subspace topology, and so on. And you can talk of the boundary of this half space, and the boundary of this half space is that hyperplane where x1 to xn minus 1 are arbitrary, and the last coordinate is 0, right? So this is a hyperplane, and this you can kind of identify with Rn minus 1. Okay, so this is the sort of the model spaces. Now, given this, what's the definition of a? We want to get to a smooth manifold with boundary, but first let's talk of a topological manifold. So here's the definition. So topological manifold with boundary is like before. It's a topological space which is Hausdorff, second countable, and this time, instead of being locally Euclidean, you want to be locally sort of neighborhoods should look like this neighborhoods in this model space. Okay, so there is each x has a neighborhood u, so that there's this homeomorphism. So let me just write. So there's this map. This is like the charts on the manifold with boundary. So this is a homeomorphism from this neighborhood u to some open set in this model space, right? So there could be points where you map to the interior of the half space. Well, I should have drawn some picture of a, let's say, let's draw the half plane case of R2. So this is sort of the line x. Well, this is sort of x1 comma 0. And so this shaded region here, I should shade it as in green. So that's this half plane, this half space. This is the case sort of n equal to 2, right? So there are portions. So let's, for example, the closed disk is some such manifold with boundary, where, of course, if you take a point inside the disk in the interior, then it is a manifold like you knew it was. So then, but then a neighborhood would map to some interior of this half space, model half space. So that's like a, that looks like a neighborhood in R2. But if you look at a point in the boundary, then you would be looking like a neighborhood of a point in the boundary of this model half space, because the open sets here, since you're acquiring open sets on the subspace topology, it's the intersection of open sets in R2 with this subset, with this half plane. So these disks, half disks, are actually open sets in this model space. Okay, so in any case, this is what a manifold with boundary is, and this is a manifold of boundary, I should add, of dimension n, because here I've kind of kept this this n to be dimension of the model space. Okay, so this is the definition of a topological manifold with boundary. Now, if you want to look at a smooth manifold with boundary, you just take such a topological manifold with boundary, and then you give it a smooth atlas. And I should mention that it's a maximal atlas just to make things, unique, right? You can might also talk of, sort of some equivalence relation between atlases as we defined before, right? So some compatibility of atlases and so on. But the maximal kind of takes care of that. All right. So so what's the smooth atlas now? Well, it's you should, so inside in interior, these points that map to the interior of the half space, there's no problem in defining smooth. But if you are at a boundary point, and you have to know what smooth means. I mean, maybe I should draw some picture. So you have maybe some. So you have to so the smoothness of the transition maps. You might have to sometimes talk about maps, from taking, let's say, a point P to a point, sort of f of P, maybe call it G of P. So these are, let's say, this is like a transition map. You want to talk of this being smooth. Okay, so you might have to define that. Well, I mean, so this is easy. So this kind of map is, so G is smooth. If there is a smooth extension, so smooth, let's say, at P. If there is a smooth extension to a neighborhood of P. Okay, and you can show that this is well defined. So in fact, I mean, so if you want to show that a map like this is smooth at the point P, where it's really only defined in sort of the one half space, right? So then, well, I mean, you say that it's smooth if it admits there's some neighborhood in, well, this is a neighborhood in, let me just say Rn, right? So this is a neighborhood in Rn of P, right? So this is, you're talking of, right now you're talking a map from Hn to Hn, but remember Hn is sitting inside this ambient Euclidean space. And so you say that a map like this is at a point P on the boundary of Hn is smooth if it admits a smooth extension. If there's a slightly larger open set in which G is defined, where it is indeed smooth, right? So smoothness and an open set in Rn you can define, and so this is so there's yeah. So anyway, so this is a little bit of a technicality that you have to kind of keep in mind, and you can show that this is well defined. Okay, so if it is an extension is not unique, but anyways, it's you just need one way to extend it. You've got probably sort of worked out how to extend maps, defined submanifolds, etc. So similar kind of thing is going on. Okay, so so that's yes.
One little question.
Yeah.
While defining a smooth function on a manifold, do we need to assume that the function is continuous a priori?
No, I don't think so. I mean, yeah, so the way that we define things, right? So I think we got continuity for free once we knew that something is a homeomorphism and so on. Yeah.
No, sir, I'm asking, suppose I say f is a function from M to R, M is a manifold, with or without a boundary, then do we need to assume that, or not R, let's say M to N, some another manifold, and then do we need to assume that this function f is
No,
continuous?
I don't think so. I don't think so, because in a smooth function, an Rn is automatically continuous, right? So we the way that we defined it, so locally we know it is a smooth function, right, at the level of charts, right?
Yeah, but sir, there is a in the book of Lee, the definition assumes continuity, or I mean a weaker version
Yeah,
of continuity.
some books might do that, but I think we are okay. I don't think we need that. I mean,
Okay.
yeah, I mean,
Sir, one more question.
but you can assume it just to be safe. You can assume it if you want to. Yeah, but
Okay.
it's automatically always going to be continuous for us. We're going to assume that it's a smooth function. A smooth map is always continuous. Yeah.
Sir, one more thing. Since we have already embedded the manifolds inside Rn or some n,
Right.
can I mean, suppose f is a function from m to some rk or maybe some n. Then, if it is smooth, can we assume that it is a restriction of a smooth function from Rn?
Well, you can extend it to a neighborhood of that embedding. You
Yeah,
can't
I mean, yeah,
you can't
neighborhood.
always, I mean, yeah, so you can't always, yeah, I mean, that's a good question. I mean, so you can't, yeah, you might not be able to always extend it globally, I think.
No. If it is even locally, then we'll also, I mean, then also the life, I mean, life will become easier because we can handle the functions on Rn pretty well.
Yeah, well, I mean, that you kind of already know how to do, right? Because, you know, you've seen that you can extend a smooth map from a submanifold to a neighborhood of the submanifold in the ambient manifold, right? This is something that was a homework problem. So yes, so that's why you can always you can think of the manifold as some submanifold of Rn, and then once you have that as a submanifold, you can extend that map or the function or whatever to a small neighborhood of that submanifold, right? So yeah, so that you can do.
Okay, thank you, sir.
Yeah, sure. Okay, right. So in any case, so there are these. This is sort of the definition of a smooth manifold with boundary, and here I should also mention that there is a boundary of M. So this is a special subset of such a manifold with boundary. The boundary of M denoted by boundary M is the set of points of M such that some chart, these charts are these U comma phi, right? So these maps, so maybe I should have called it chart somewhere. So this is sort of the chart. The local charts are now to the model space Hn, not Rn. So that some chart maps. So maybe let me sort of not write it. Let me sort of write it with slightly more mathematical notation as a set of points P and M, so that some chart phi takes P to a point in the boundary of the model space. Okay, so just like in that first example that we had of a closed disk, right? So each point in this circle, that sort of the boundary of the region, you have each of these points have this property. There's some chart that maps it to the boundary of the model half space. Here it's just the two-dimensional half space of the half plane, right? So this point goes here and so on. Okay, but if you are in the interior, then if you look at a neighborhood, then this neighborhood will map to the interior of the half plane, which is the model space here, right? So that doesn't go to a point in the boundary. So this sort of is the boundary of the half plane, and the interior is somewhere inside. Okay, so so the set of points that maps to sort of these charts, take them to the boundary is the boundary of, is defined to be the boundary of M, and you have to check that this is well defined. Okay, so note this is well defined, since you know, you can't have a chart that takes it, if something goes to the boundary of the model space, of the half space, you can't have another chart that takes it you to the interior of the half space. And this is because transition maps are diffeomorphisms. So so there is no, let me just say, there is no diffeomorphism that that takes a boundary point in this model space. So let me write it properly. So in to an interior point in the model space. Okay, so so in other words, I mean, suppose you have some phi, so some phi that takes the point P to the boundary, and some psi that maps into the interior. Then if you look at psi inverse phi, or the other way around, it will be a map from an open set in Rn to an open set in Rn. Remember that, you know, this will be a smooth map, and smooth maps can, by definition, things that can be extended to an open set in Rn here, and so this would take. So what would it take? So sort of the interior is something like this orange guy that I drew over here. So this map psi inverse phi could be something like this, right? So here let me I mean, let's imagine that you have phi and psi. Let me just sort of redraw these arrows. So suppose you have these two. Somehow there is another kind of chart sort of for the same point P, so which maps to the interior, right? And so then, so one of them is phi, the other is psi. And this is the transition map, right? And this transition map, what does it look like? Well, it takes this open set here. So it's a smooth map here. This domain is now an open set in Rn. So it's a smooth map on an Rn, and it takes it's a smooth map, and it takes this smooth map to this half disk. Okay, in Rn, and it's not just a smooth map; it's a diffeomorphism, right? So the point about yeah. So anyway, so it's these transition maps are diffeomorphisms because they have inverses also, which are smooth. So there's no diffeomorphism that takes this open disk to a half disk. I mean, so the image under, so now we're talking of diffeomorphisms of open sets in Rn to open sets to Rn, right? So the image of any such diffeomorphism has to be an open set, whereas here this is not an open set in Rn. Okay, so maybe let me just write that down. So so this is this maps an open set into a subset. So is a diffeo that maps an open set into a subset that is not open, which is a contradiction. Okay. So you can't have charts both to an interior point of the model space as well as a boundary point. So this makes this boundary well defined. Okay, and a fact, let me also mention a fact that the boundary of a manifold with boundary is always a manifold. It's a smooth n-1 manifold. If M was n-dimensional, this is one dimension less. And this is not going to be a manifold with boundary. This is just a smooth manifold, n-1 manifold in the usual sense. And the way that you see that it is a smooth n-1 manifold is you just restrict the charts of M to the boundary. So in other words, remember that so if you have u phi, some chart of M, then and suppose and here by chart I'm kind of really mean something that intersects the boundary, right? So sort of u looks like this, all right? And so then so this is a chart of M such that u intersection boundary is non-empty. Then if you restrict we know that this maps to a model space, sort of the half space, right? So then if you restrict your this map phi, this chart to that intersection with the boundary, then it will take u intersection omega to this some subset of to this boundary subset, right? So this red portion goes to the red portion. But what's the red portion lying inside? Well, it's lying inside the boundary of Hn, which is Rn-1, right? So these charts, if you restrict them to the boundary, you get charts to Rn-1. And so this is how you can an atlas on M, a smooth atlas on M. If you restrict it to the boundary, you get an atlas for the boundary of M. And this time it's mapping to open sets in Rn-1, so you get an n-1 dimensional manifold. Okay, so that's how it's. So this is often a useful fact, and it's something that will come up quite often. All right, so one way of producing manifolds with boundary is to take these pre-images of sub-level sets like we were doing. So, sorry, to consider sub-level sets, so sort of pre-images of, instead of points, we take pre-images of intervals. So let me just say what I mean. So one way of producing manifolds with boundary is to do the following. So you take you let's say you suppose you start with something which is not a manifold. Well, it's not, doesn't have boundaries. So let M be manifold without boundary, and suppose I have a function on it, and let f from M to R be a smooth function, and suppose that 0 is the regular value for that function. Okay, so then we know that the pre-image of 0 is a manifold, but if you look at the pre-image of the interval from starting from 0, including 0, let's say to infinity, so this is going to be a manifold with boundary, assuming, of course, that, I mean, this function takes positive values as well. If it just yeah, anyway, so, and the boundary so let me call this n, and the boundary of n is f inverse of 0, which we know is a manifold. Okay, so, well, this is the sort of, this is one way that you can produce these manifolds with boundary. If you take, instead of taking inverse images of single points, you take inverse images of these intervals, or in this case, this, I mean, these rays, basically, right? So this is from starting at 0 to go all the way to infinity. Okay, so
Sir?
Yes.
Sir, to know a point is a regular value or not, we need to know the tangent space of the tangent space at each point of the pre-image of that point, right?
No, this is, yeah, this is a manifold without boundary, right? And so you know what a regular value is, right? A regular value is something which maps, you know, level of the tangent space, it is surjective, right? That's the point.
Okay. Sorry, I did not notice that it is without boundary.
Yeah.
Sorry for that.
No problem. Okay. All right. So now, so you can generalize many of the things that we were doing in this context. So, for example, Sard's theorem in this context. So for manifolds with boundary is, you can sort of you can think of, let me just say, just right in this context, is you can think of this as saying that for any smooth map f, now from this is a, let's say it's a manifold with boundary now, so this M is a manifold with boundary to n, and this is, let's say, not manifold without boundary. Manifold without boundary is sometimes called a closed manifold, sort of without boundary. Almost every point of n is a regular value of both this map, both the map M to n and of the map, the boundary map from the boundary of M to N. Okay, and so yeah, so here you have to kind of right. So maybe one has to kind of try to understand what it is to be smooth at a boundary point, but yeah, so right, so it's sort of it's being smooth at the boundary point is just to kind of think of it as a map, this restricted map. This is sort of somehow the restriction of F to the boundary, right? So this map is just the restriction of F to the boundary of M. And so if this map now, so since this boundary of the manifold is a manifold in its own right, you can think of, you can talk of smoothness of this map, all right? And so so in any case, I mean, so you can sort of, you can think of this map from M to M, you can think of as sort of two maps. It's a map of, maybe I should say interior here, just to make it clear. So you can think of it as a map from the interior of M to N, together with this map from the boundary of M to N. Okay, and so you got these two maps from smooth manifold to N, and so each of these you can talk of, being a regular value, something being a regular value. And so for each of these, the usual Sard's theorem that we've seen tells you that the set of regular values is sort of a full measure set, right, in N. And if you take the intersection of these two full measure sets, you again get a full measure set. So almost every point of N is actually a regular point of both maps. Okay, and so if you take the pre-image of such a map, and maybe let me just continue with this. So in fact, if y in N is a regular value, is such a regular value, then F inverse of y is going to be sort of, typically is going to be a manifold with boundary. And the boundary of this manifold is going to be, maybe just, so the notation might become confusing. Let's call this N. And the boundary of N is actually the pre-image y intersected with the boundary of N. Okay. Maybe sort of, let me draw a picture to sort of have something. So, I mean, for example, what's an example? I mean, you could have a situation where you have, let's say you have, let's say your sort of manifold with boundaries, this infinite, semi-infinite cylinder. Okay, so this is sort of going all the way to negative infinity, if you like, and this is sort of, let's say, this is sort of mapping to the circle, right? So they're somehow projecting down to the circle. Okay, so this is sort of S1 cross 0 infinity, mapping down to the circle. So then what's the, you can check that this is a satisfying. So any point here in the circle is actually a regular value in this stronger sense. And what's the pre-image like as well? The pre-image is going to be something like this whole line together with this point here. Okay, so this is not quite a nice example because, typically we would look at compact manifolds with boundary. So but this is, it's a non-compact thing. Maybe I should just sort of make it a finite cylinder. Let me just make it into a finite cylinder here. So let's say, so this is S01. Now it's compact. Okay, this is a finite cylinder and it's sort of projecting down to the circle. and then and so this time, okay, so this is sort of behind us, so maybe I should draw a dotted line. Okay, and so this time the sort of the pre-image of any such point is one of these longitudinal lines, right, which is an interval, right? So this is this sort of the manifold here, which is the pre-image. So this is like our y in the theorem. And so F inverse y, which is our n, is really sort of diffeomorphic to a closed interval. And the boundary of that thing is the union of these 2 points, right? Sort of somehow this is sort of the 0 end point, and that's the other end point. And these are exactly the intersection with the boundary of the original cylinder. The boundary of the original cylinder, the 2 boundary circles on either side. Anyway, so this is an illustration of what I mean by this. All right. And
Sir, could you please update the notes once?
Okay, sure. Yeah, if you want me to scroll back or something, you can always ask me to do. Okay, so anyway, so this is an illustration of this. In fact, here, let me also mention a fact before I get to this. So there's a sort of a useful fact to know is that it's black. So any compact connected one manifold with boundary. By the way, manifolds without boundary also can be thought of as manifolds with boundary, except the boundary is empty. Okay, so any compact connected one manifold with boundary is diffeomorphic to either the closed interval 0, 1, as we just saw, or it's a circle. Okay, this is a sort of a classification of smooth manifolds with boundary in dimension 1. Okay, so it turns out that up to diffeomorphism, there are only sort of these 2 examples of a manifold with a compact manifold with boundary, compact and connected. Of course, you can take disjoint unions of such of these guys, and they are also going to be a compact one manifold with boundary. Okay, and one consequence of this is that the boundary of any compact one manifold with boundary, where I don't assume connectedness, has an or is a finite set, of points, and there are an even number of points. This is actually very useful to know. Okay, why is there an even number of points? Well, each component of that compact one manifold with boundary would either be this interval or be the circle. Now, the boundary of the interval has 2 points and the circle has 0 points. So if you add up all the points that appear, the boundary would always be a 0 manifold, and the 0 manifold is just a point. Okay, and so the so the fact that it's a finite set of points is easy. I mean, just compactness tells you that it has to be finite anyway. But the fact that it's even depends on this classification of one manifolds, like we had here. Okay, so it's either 0, 1 or S1. Yeah, you can find a proof of this, by the way, in sort of Milner's book, I think. Sort of topology from a differentiable viewpoint. So I won't get into the proof of this fact, but it's not so difficult, right? Okay, fine. So so anyway, so this corollary is something to keep in mind. We are going to try to use this also. So here's another application. Now that we've introduced manifolds with boundary, I wanted to tell you about the no retraction theorem. You might have seen this in topology. So let me actually to sort of remind you what it is. So there is no retraction from well, let me just say where you might have well, from Dn to the boundary of Dn, which is Sn minus 1. So Dn is the closed ball. Let me just say that this is the closed unit ball in Rn. So no retraction, okay? And so what does that mean? That means that there is no continuous map f from Dn to the boundary of Dn such that on the boundary it's the identity map. Okay, so this is what a retraction is. And right, so anyway, I don't know whether you've seen this. Have any of you seen this theorem, no retraction theorem?
In algebraic, yes, in algebraic topology.
Yeah, that's right. Okay, so yeah, you would have seen it in algebraic topology. Exactly. Yeah, I guess not all of you have done algebraic topology, but anyway, this is one of the theorems you encounter very quickly when you learn about homology and so on. Anyway, so we can prove this using all these basically Sard's theorem, but as follows. So you can say that so you can prove the following fact, and this will follow from this. So you can prove the following. So if you look at M, a compact, let's say smooth compact manifold, well, I should say compact smooth manifold with boundary, and so then there is no, let me just say, there is no retraction. Let me call it smooth retraction. So it's general in one sense that I'm now not just looking at a specific example of a smooth manifold with boundary. It's any smooth manifold with boundary. But on the other hand, instead of a continuous map, I'm looking at smooth map. And this is saying that there's no smooth retraction from, let me call it G. So there's no smooth retraction G from M to the boundary of M. Okay, and what's the proof of this? Well, suppose G M to M is a smooth retraction. Let Z in the boundary of M be a regular value. This is guaranteed by the Sard's theorem. So such things exist and they're full measure in the boundary. So then, so from what we just saw, then this G inverse of Z is going to be a submanifold of M with boundary. So let me just say this in a slightly different way. So let's give it a name. So then sort of the pre-image is going to be a submanifold with boundary. So that so then this N is a manifold with boundary, and is a submanifold of, well, and this is sort of from what we discussed. The boundary of n is basically G inverse of Z intersected with the boundary of M. Okay, and what is the dimension of n? So the dimension of n is 1, right? That's just because you know, so the dimension of M, if it's n, the dimension of boundary of M is n minus 1, right? So let me write it somewhere. So if this is n, this is n minus 1. So remember the way when we proved that, you know, sort of the pre-image theorem, so the dimension of that pre-image, that submanifold we get, is the difference of the dimensions. Here the difference of the dimensions is 1. Okay, so you have a one-dimensional manifold with boundary. It's also compact because we assume that M is compact. It's some kind of subset, closed subset of that of M. So it's let me just mention that here. It's also compact. N is also compact. So we know that it's a union of intervals and circles, right? But so another thing that we do know is that so since so it's identity on the boundary. This is where we use the fact that it's a retract. This is actually equal to just a point Z, okay? Because remember, we are looking at all those points in Z that will map all the points in the boundary of M that maps to Z, right? But the only point that maps to Z, the boundary is Z itself, because it's the identity map on the boundary. So this is where this equals this, since let me write that separately here. Sort of note that the boundary of n equals G inverse of Z intersection with M equals Z, since G on the boundary of M is the identity map on the boundary. Okay, so so this is a contradiction because the boundary of this a compact one manifold has to have an even number of points, and here we just get 1. Okay, so that's a contradiction. Contradiction to the corollary above. Okay, so once you know Sard's theorem and the classification of one-dimensional manifolds, you prove this smooth retraction theorem, right? So you can show that there's no smooth retraction from any smooth manifold with boundary to the boundary. Okay, and from this one can actually also get back to our sort of the theorem that you've seen before about continuous retractions from the closed balls to the boundary, because you can approximate a continuous map by smooth map. This was another one of these homework problems that you had, right? So let me not give details, but let me just say some things about how that's done. So the same. So this implies the no retraction theorem for Dn, sort of mapping to the boundary of Dn, as follows. So you can, first of all, if you're given a continuous retraction, so suppose you're given suppose f dn to dn, boundary of dn is a continuous retraction. You can first, you want to find a smooth thing that approximates them, but it should approximate it in a way that it's still, identity on the boundary, right? That's what you need. And so the approximation that we saw earlier, where you kind of you sort of replace open, take an open cover, it's a small enough open cover, and you kind of find some smooth map epsilon distance away. That might sort of be worrisome near the boundary, because if you want a specific thing on the boundary, and if you don't want something epsilon distance away from the identity map, you want identity map on the nose. And so anyway, so one way to sort of, one intermediate step that helps to guarantee that is, so you define a new retraction H. It's going to be still continuous, but it's going to be not doing much in a neighborhood of the boundary. So so that is, and it's going to be smooth there, well, in particular. So that is smooth in a neighborhood of the boundary. Well, the boundary is Sn minus 1. Let me just say boundary. And how do you do that? This is some kind of a trick one can do. So one can define this to be, one can extend that identity map a little bit inside. And everywhere else you do, so you kind of change the map radially, if you like, and you kind of sort of radially whatever, well, sorry, I call that map F. Maybe I should call this G. So suppose G was a continuous retraction. I define this map. So radially, it's going to do whatever G was doing, but at double the speed, so that somehow maybe this is the picture. So you have this smaller disk, so that half the disk it's sort of doing what it was doing, and after that it's sort of basically the identity map. Okay, so so this you can do to that original continuous retraction. So the 0 less than x less than equal to half, right? And so now at least in that in a neighborhood, in that shell between radius half and radius 1, it's actually going to be smooth. And then it's easier to approximate this by a smooth map that agrees with H in a neighborhood of the boundary. Okay, so then approximate H by a smooth map. Let's call it H hat dn to Sn minus 1, that, and agrees with, so you don't have to change the map in a neighborhood of the boundary, agrees with H in a neighborhood. You can use, sort of bump functions and things like that, because it's already smooth there, and it's already identity on the boundary. Okay, so now so if you do this, you get a smooth retraction. So this H hat is a smooth retraction, and now you contradict the theorem that we just proved. Okay, so all right, so you're starting from a continuous retraction, you get a contradiction basically. All right, and so so this is one remark that you can actually produce, prove that this is sort of one reason why these approximation theorems are useful. Right. So the second remark is is just to remind you that why this no retraction is useful. Maybe this is just to sort of remind you that sort of the so no retraction for maps. So no retraction theorem for dn to the boundary of dn, sort of no continuous maps, implies the Brouwer fixed point theorem. This is sort of the key step, the key ingredient in showing the Brouwer fixed point theorem for. This is where you might have seen it in algebraic topology. Oops, let me just write it properly. Brouwer fixed point theorem for continuous maps dn to dn. So any continuous map from a closed ball to itself has a fixed point, right? So anyway, so this gives so proof without homology and things like that. Depends on Sard's theorem and the classification theorem of compact one-dimensional manifolds. Right. So there are, I mean, these approximations of maps can be extended to approximations. So approximating a continuous map with a smooth map can be extended to approximating continuous homotopy of maps that we have seen in algebraic topology with smooth homotopies. Okay, and then so and again, one basically uses Sard's theorem to show that one can do that in a nice way, etc. And so I won't get into transversality and all that, but that's one sort of direction in which this course could have gone. I could have talked about transversality and intersection, and do a lot of these algebraic topology things in this smooth category. So what we are going to do next is sort of go on to talking about vector fields and then getting to Lie algebras and then sort of trying to go towards the classification, the sort of the theorems of the fundamental theorems of Lie theory, basically, is just the sort of the correspondence between Lie groups and Lie algebras and so on. Okay, so so we won't go into too much of all this transversality. I mean, we're not going to go there at all. But if people are interested, I mean, this is some so what we just did is something that goes by the name differential topology. And so, for example, there's a book of Hirsch, Morris Hirsch, I think, on this and so on. There are other books also. I mean, Guillemin and Pollack, which is listed in the course website, is also another nice book which talks about some of these things. Right. So, in any case, this is something you might sort of go into if you're interested in. We won't be doing that in our course. All right, let's stop here. Next time, then we'll start with vector fields and